as well as it was said, I'm currently a researcher at DeepMind, and I used to be the statistician at Optimizely. I think at some point there were two of us, but I was responsible for all the statistics there. And Optimizely, at least when I was there, was a small San Francisco-based startup that basically was trying to democratize experimentation. So they would install, I guess, software on their client's one page that lets their customers run experimentation, then they would collect the data and then present it in a dashboard. And kind of importantly, Optimizely was all in on this sequential hypothesis testing, which I'm sure you've heard a lot about so far. So they issued the fixed horizon t-test because basically the people there before me observed that everybody was peaking and kind of abusing these statistical tests. They thought we're going to actually build a platform that took into account the use case. So they used sequential hypothesis testing, basically a simplified version of all the sequential hypothesis tests you've seen so far today. And that's was, I guess, one thing that differentiated them from the rest of the market. So as a statistician, I kind of saw a lot of pitfalls, got to interact with a lot of customers. So hopefully I will be able to convey some of the gathered wisdom there today. So my talk, basically the first 2/3 will be about causality. Like what is causal inference? What is the role of causality? How is causality and experimentation trying to answer the same question? And then the last third will be trying to share some insights and kind of convince people to have better practices when it comes to actually running experimentation, running t-tests when you're doing experimentation in your own platform. Okay, so let's get started with an example. And this is the causal inference bit. So here's a specific example that I guess we'll guide our introduction to throughout the first talk. So our developers went and they basically designed a new user interface that presents advanced options to the user. So the old status quo is on the right, where you see these like advanced options have been kind of are not shown by default. They've been they're not split by default. But the new design on the right, all the advanced options are available and shown to the user. And our designers have made this and pushed it out to the beta customers, and then we've been collecting data for a while. And one thing we'd like to do is, maybe we're not trying to run an experiment right now, but we have a lot of data, and our question is, can we actually decide whether to deploy these advanced options to everybody, to all our users, from the observational data alone? And when I say observational data, I mean data that we just kind of passively collected, where in particular users have, in some sense, self-selected whether they get the control of the treatment. So we have a program for a beta, or people can sign up, users can sign up for a beta user or to participate in the beta program. And if they're in a beta, then we roll out the advanced features to them. So there's some correlation between the user preference and whether or not they see it as advanced user. And a common way of modeling users that I've seen used successfully is to think of users as belonging to two groups. One, which is regular users, so if that's just your typical user, but the other is power users. And if you're on your webpage, you probably know who your power users are, but they're the ones who spend more money, who've been at the platform longer, who tend to appreciate things like being on the cutting edge and getting beta features, or tend to appreciate more options and control over their decisions. So that's kind of the idea. Now, in order to step back and model all this, we need a couple of mathematical tools. And it seems a little strange to talk about what probability is, this late into the day. Thanks for sticking around so long, by the way. But I used to see a lot of confusion. People weren't exactly sure what was meant with the probability. Sometimes I heard people describe it as a belief, or sometimes they would describe it as some other event. But for the purpose of this talk, you can think of a probability as proportions on some population. And this is my kind of favorite view to explain to people, where you imagine in some Platonic cave, you have all the users in the world, the users that you see and the users that you haven't, and that's like the collection, that's the population. For each user, there's 3 attributes that you care about, at least for the purpose of this study or this example. We have U, whether that user is a power user, so that's a binary. We have A, whether that user has seen these advanced options, that's also binary. And we have S, the difference in spend in dollars, whatever currency you like. And probability distribution kind of defines the demographics on average of this population. So in our mind, we have this little collection of little gray stick figures, and each stick figure has these three attributes, and they occur in some proportion. And when we talk about the probability of events, like the probability of A is equal to 1, we're asking about the proportion of users in this hypothetical population that happen to have seen the advanced options, A is equal to 1. We can also ask more nuanced questions, like what's the probability of U is equal to 1 given A is equal to 1? So of all the users in the subpopulation that have seen the advanced options, what's the proportion of them that are power users? And we can calculate this, and that's just asking a proportion in a subpopulation. So I think this makes probability very concrete. Okay, so that was the easy part. The hard part that's probably a lot less familiar to people is a causal model. So the question we want to answer is, should we add advanced options to everybody? That's a causal question, because right now, the current status quo, at least in our example, is that some users see the advanced options, some users don't, and there's some complicated relation between who gets to see the advanced option and who does not. So we're asking, in a hypothetical world where we actually turn on the feature for everybody, what will happen? Right? So this hasn't been the data that's collected yet. So we want to try to infer what's happening in this hypothetical world. And whenever you're doing experiments or testing product launches, that's what you want, right? You kind of have a small experiment where you collect some data, and then you're trying to infer what will happen if you then change the state of your platform, if you turn advanced options on or offer on for everybody. So in order to do this, we need to understand how these variables, these attributes relate to each other. So I've drawn on the right a directed graph that kind of indicates what attribute causes what. So here we see that U has two arrows, one that points to A and one that points to S. And this is telling us that a user's chance of having seen advanced options is determined by whether they're a power user or not. And this seems to really follow from the story we have, where power users like beta options, and we've rolled out advanced users to those enrolled in the beta. So if you are a power user, you're more likely to have seen the advanced options. We also know that power users spend differently, which explains the arrow from U to S. And finally, the red arrow, which is kind of the arrow that's most important to us, is the effect of seeing the options has on the spend. Right? And in that case, that's kind of arrow, it goes from A to S because that's the flow we have in our mind, where a user will see an advanced options and that'll affect whether they want to spend more or less money. It wouldn't make any sense to have the arrow in the other way and claim that, say, a event S that happens in the future somehow caused the user to see advanced options in the past. That's like an acausal method. So these arrows kind of encode our causal understanding of the problem and kind of let us predict what will change when we make changes to the system. Another way to say it is, if we could change one attribute, what would we expect to change? So if you could change U, what would we expect the spend to change? So if we were to say, if we were to toggle U, would we expect the spend to change? Apparently, yes, we'd also expect the chance of the attributes to change. But if we were to change A, we would expect the spend to change because of that arrow, but we wouldn't expect U to necessarily be influenced by whether users saw advanced options or not. And in causal inference, one of the starting points is always with a causal model. These typical graphical models are very common in the Perl setting, but they, as I said, encode our causal assumptions as to what's actually happening. Typically, causal models are something that you write down. In this case, it's kind of our intuition or understanding of the problem. In other cases, like in biology, for example, causal models can be developed by domain expertise, or sometimes you can establish them by running experiments. But it's always a starting point. Okay, so let's be a bit more concrete and actually give some numbers here, which will let us kind of make a point later on. So we're going to specify what this model is. So for our cartoon example, we're going to assume that power users are less common, which generally tends to be true. So the probability of U is equal to 1 is 1/3. So the probability of U is equal to 1 is 2/3. We're going to assume that power users love new features. So in particular, if you're a power user, the chance that you've seen the new feature, i.e. because you added yourself to the beta program is 8/12, which is pretty high. But on the other hand, non-power users aren't opting into the beta, so the probability that you've seen the new advanced options given that you aren't a power user is much smaller, 5/12. Power users also love options. So the expected, so S is the increase in spend, but the expected increase in spend of all power users who've also seen the advanced options is pretty large. It's $45. They're very excited about the new options, and it causes them to just buy more. Or maybe they take some extra options that have extra fees associated with them. So that's how you increase the spend. On the other hand, regular users get confused easily, and they tend to leave the checkout flow. So the expected value of S for all users that aren't power users but have seen the advanced options is actually negative because you've driven people away from the platform. And finally, the status quo is the expected value of S given A is 0. Okay, so this is the full model, and now we can start making computation with this. And the first question, of course, we want to ask is, what do we do with our observational data, right? We've collected data, like say a week's worth of data from this process. And before we actually answer questions, I'd like to point out that we can very easily make calculations. Here, I just putting this calculation on these slides, which you can verify later, but we can calculate the probability of A is equal to 1 is a half, because I conveniently choose a number, so that would work out. And the probability of U is equal to 1 conditional on A is equal to 1. So the probability of power users in the subpopulation of all users who saw the advanced options is 4/9. And if you recall, just up here, the baseline level of power users is a third. So in the subpopulation of users that have seen advanced options, the power users are overrepresented. They're 4/9, whereas if there was no connection, they would be 1/3. Okay, so we have some data, right, in the form of tuples A, I, U, I, Si. And the first quantity you might be tempted to look at, one that's very easy to calculate from the data, is what's the empirical mean? That's what this E subscript N denotes. The empirical mean of the difference in spend of all users in your data set that have seen the advanced options. I want to take that empirical mean and subtract from it the empirical mean of all the users that haven't seen the advanced options, right? And that's just what I've written down here. I'm hoping you can see my cursor actually, but so this is an indicator function that's basically when you sum over I, so sum over all users, is just selecting, this is 1 for when this is 1 and 0 otherwise, so you're just selecting the SIs that correspond to users where I is equal to 1, and you're subtracting from that the SIs where the advanced options were not, so where AI is equal to 0, and dividing it by the appropriate counts. Okay, so we can calculate this very easily from the data. And this is, in the data we've seen, the difference between the average spend of the users that have seen the advanced options and the average spend of the users who haven't seen the advanced options. So one might think this is a pretty good proxy for for what would be the difference if you were to give everyone the advanced options or using a probability model, we can calculate the exact form of this expectation, and this estimator that we have will be very similar to it. And this is just equal to the change in spend for advanced users with power, power users using the advanced options times the probability of the user being a power user conditioned on the subpopulation of A is equal to 1. That's just 4/9. That's the calculation on the previous slide times 45, plus the change in spend of non-power users who've seen the advanced options, which is minus 27 times that relative proportion, which is 5/9. So in total, that's equal to $5. So this kind of suggests that perhaps adding advanced options to everybody would be a good idea because we've seen in our data set that the average spend is $5 higher for users that have seen the advanced options than for users that have not seen the advanced options. Okay, so that, now, as I've mentioned before, as I've mentioned before, this is what we just calculated is something that's purely observational. It's something we just saw from correlations in the data. And what we're really trying to ask is a counterfactual question. It's what happens if we change the mechanism, if we change the world we see to be that everybody gets advanced options, what's then going to happen? So I'd kind of like to have a little audience participation. and ask everybody what they think is going on. So I actually don't know if I can see everybody while also sharing. So I'm hoping someone, Maestro, perhaps will be able to tell me roughly how many people are raising their hands when for these three options or these four options. I've copied on the right all the probability in case you've forgotten the numbers. But the question is, what will happen if we change A is equal to 1 for everybody, for all our users in the population? And there are four answers. So if you could, it's possible actually see, let's see, oops. Well, I'm just going to ask and then hope someone takes the microphone and helps me out here. If you could give me a rough sense of how many people are raising their hands for option A, which is we will actually see a $5 increase.
Will do. So $5 increase, anyone?
Yes.
How many hands? Nobody.
Nobody. Oh, so they smell a trick question. What about for option B? The increase will actually be more than $5.
More than $5, anyone? You guys all know the right answer? Okay, again, nobody.
What about option C?
C. I have 1, 2, 3, 4, 5, 6, 7, 8. 8 people.
Great. And what about option D?
The rest says the event will decrease.
Now the question is, so that's actually the right answer. Good job, team. The question is, did they just do that because of the trick answer, or did anyone actually run through calculations in their head while I was asking the question? Well, we'll answer that another time. So thanks for your help. So yes, that is the answer. The spending will actually decrease. So we actually get an opposite answer, which perhaps you've seen could help or guess that this was set up as a cautionary tale, but still let's perhaps go through the language of causal inference and why this actually is the case. So what we're trying to calculate in this counterfactual world is not the probability of S conditioned on A, but it's actually this what's known as a potential outcome. So it's a probability of S, the potential outcome, which I've written S subscript A is equal to 1. So this is a new random variable S where we have altered the world by setting A is equal to 1. So this is known as an interventional quantity because we've intervened and we've changed A. And this probability, the expected value of this rather, is just the expected value of S conditioned on A is equal to 1 and U is equal to 1 times the probability of U is equal to 1, plus the same with U is equal to 0. Right, and working that out, that's just a third times 45 minus 2/3 times 27, so we get minus 3. So as maybe some of you aren't surprised, but I still think this is a good example to really see is the answer has changed, right? So looking at the observational data is not sufficient for answering interventional or causal questions, which perhaps is obvious now that I've said it, but beforehand it's kind of hard to know sometimes when you have these sort of effects. And in terms of this causal model that we've been talking about, we can represent what S subscript A is equal to 1 is with changes to this causal graph. So remember, we used to have all these nice edges, but in this new world where we've set A is equal to 1 forcefully, we no longer allow A to be determined by U. So we've cut this link, this kind of grayed out link here. And that's the really important intuition is that in this this intervening variable, we have like so-called mutilated the graph by removing this edge by just setting A to not be a function of its parents. So after doing that, we have defined a new distribution for S, this new distribution which takes on the value generated by this graph, and then that's the S that we actually care about answering questions about. Okay. So put another way, just to really drive down this point, this is just an example that correlation does not imply causation, right? In this correlated graph, we have this is the data that was generated from observational distributions. And what we really want to do is answer a causal question, which is the graph on the right without that edge. And to kind of drill down a bit deeper into what went wrong, when we calculated this expected value on the observational data, we've actually, you saw that when we use the law of total expectation and sum up the expectation of S conditional on A is equal to 1 and U is equal to little u, we multiply that by the probability of U conditioned on the subpopulation. of U is equal to little u conditional on the subpopulation. And I commented earlier that in this observational data, the proportion of power users in the users that seen advanced options was much higher than it was on average, right? This is 4/9 versus the population as a whole is 1/3. So we've basically overrepresented the power users, which led us to basically over count their bonus in spends, and that's why we got the wrong answer. So, what can we do in this case? Well, there's two solutions. Yes, so the term for this is confounding. So U has created confounding between A and S, which pops up a lot, and it's always important when you're dealing with observational data to know what sort of confounding you have, or at least be very aware of what confounding you have. And kind of put another way, confounding is when your treatment, in this case S, and your response or your outcome, your treatment, which is A, and your response S, have some common cause. And the reason why confounding is dangerous is because if you, in your observational data, see a strong correlation between A and S, you're not certain if that's because A is strongly affecting S, i.e. if the red arrow kind of is strong, or if they just both happen to be correlated via U. So you have to make some adjustments to try to correct for this confounding. And there's kind of two ways to get around this, really. Fundamentally, there are two ways that people have used. The first is to actually estimate the causal effect. So on the left is the estimator that we had for this conditional probability or the conditional expectation, and that's wrong, but you can actually use knowledge of the causal graph to write an estimator that's correct. So this is just on the right, the inverse propensity weighting estimator. So unlike the incorrect estimator that just looks at the conditional probability and it sums up the correct SIs divided by the number, now you're actually weighing them by 1 over the propensity. So the propensity is the probability of treatment given the covariance, U in this case, right? And this gives you an unbiased estimate. The nice thing about the IPW is that you can calculate from observational data. The not nice thing is that, of course, you need your causal model. And in particular, you need to know some sort of sufficiency condition on U, that sort of U, these covariates that you've seen are sufficient to allow you to calculate a propensity. And sometimes that's kind of a big assumption. And the second solution, as you probably all know, being at the A/B testing workshop, is actually randomization. So what does randomization do in this causality graphical model story? Well, it alters the environment by breaking this correlation. So when you do a randomized control trial, you replace whatever law was governing A with just a random coin flip, and you get a new random variable, which we call S subscript RCT, that indicates the distribution of S when you replace the observational distribution of A given U with a coin flip. And then with this new data from this new model, you've broken this correlation by randomization, and then you can just calculate, say, the average treatment effect as a difference in means. It's just the mean of SI, not of the original observation SI, but of SIs collected from the RCT, minus the mean. So this is the collection of SIs when A is equal to 1 minus the average of SIs when A is equal to 0. I'm at the average in the first case. But that's, I think, the really important intuition here is that the randomized controlled trial breaks these correlations and breaks the confounding. It's what allows them to work so well. Okay, so just to kind of quickly summarize, in causal inference, so what's the difference between these two sides of the same coin, right? Or these two solutions to the same problem of confounding? Well, causal inference is nice because observational data is easy to collect, and sometimes you can only collect observational data. So if you're, say, trying to see the effect of smoking on lung cancer, you can't make that experiment because then you'll probably be giving people cancer if your hypothesis is true. But you can collect these like smoking rates and lung cancer rates and a bunch of other covariates and then try to do this analysis yourself. The problem with causal inference, of course, the big problem is it requires strong assumptions on the causal model. Sometimes it requires a causal model, but even if you're dealing in the weaker, or in the, I guess, in the potential outcomes, not weaker or not, but in the potential outcome setting, then you need some sort of ignorability assumption. So in our case, the ignorability assumption says that this potential outcome, S subscript A is equal to little a, is conditionally independent of your treatment given your covariate. So it's conditionally independent of A given you. And sometimes these, and often these assumptions are actually kind of impossible to verify. You just have to hope that you got enough U so that you can get this ignorability claim. In the language of Perl, this says that U blocks all backdoor paths. And kind of remember, there's this story that the information flowing from A to S flows both directly through red and also indirectly. So you need to condition on U to remove this sort of indirect correlational information. Causal models can't be used from observational data, which is kind of a bummer. You have to use domain knowledge or hypotheses or maybe some experimentation to learn it. But that being said, several different communities have gone very far with using causal models and doing observational studies. And I would look at econometrics and social sciences because they tend to not be able to run experiments, so they only have observational data. So on the flip side, we have experimentation. Everyone here is very familiar with experimentation. It requires some tooling, it's costly, could have some opportunity costs. And more importantly, experimentation is very easy to abuse. If you peak or do multiplicity correction or something, you need to stick to your methodologies. And I guess that's the second part of the talk. You don't need any assumption on the causal model though, which is good because you break this correlation through an intervention. And the biggest thing is that this handles unobserved confounders. So in this causal inference case, even if you knew that there was a U there, but you don't observe it, then you're still kind of stuck because you can't actually identify what the effect is. But because the randomized controlled trial is breaking this association, it works for whatever confounders you want, which is why it's the gold standard. Okay, so I guess I should probably save questions at the end, but I'll kind of forge ahead and talk about the 3 pitfalls I've seen when I was a statistician at Optimizely. Part of my role was talking to customers a lot, so I've seen a lot of mistakes and a lot of confusions, and hopefully these will be useful lessons, if not to you, then perhaps to your team of people actually making experiments. The first pitfall is peaking, and I'm not sure if people have mentioned this specifically. I know this workshop had a lot of sequential hypothesis testing methodology, and sequential hypothesis testing is great because it's immune from these sort of problems. But if you were to go and build a sequential or build a testing platform on your website or on whatever your production stack right now, the simplest thing to do would be to do a 2-sample independent t-test. And what is tempting to do is to collect some data, calculate your p-value, plot it, and then collect more data, calculate another p-value and plot it, and then watch your p-values as they go down. And as soon as they're low enough, you declare victory and say that your test was significant. But t-tests are a fixed sample size, so you can only look at the data once, essentially. The guarantee that powers the t-test, the confidence interval, isn't designed to provide this guarantee multiple times. You need to pick a sample size, collect enough data to get there, and then look at the data once. And if you do it any other way, you don't have a false positive guarantee, right? And by false positive, that means it's when you actually declare that there's a difference between your null alternative hypotheses when there isn't one. A common misconception I've seen is that if you look at your p-values and you see it decrease really, really quickly, that's because your test was really significant. That's because your effect was much larger than the minimum detectable effect that you put into your calculator. But that's not necessarily the case. If you see your p-values drop off really quickly, it could be an AA test that you got unlucky with. It doesn't necessarily indicate anything about the size of the effect. So to really hone this in, I kind of want to give everybody a pop quiz. And here I have 2 tests. I ran these simulations. One's an AA test, one's an AB test. They're just independent unit normal, a standard normal, where in the AA test, they're both 0 mean, and the AB test, one is 0.1 mean. And the question is, if you're running your test and you've run it for some amount of time and you stop now, can you tell which is the AB and which is the AA test? So I might ask for a little help with audience participation again, to make sure people are still kind of awake. And if you think it's the first one, if you think the first one is the AA test, please raise your hand.
First one, AA test? Just a few hands.
And what about the second one?
Quite a few more.
Okay. Well, people are lucky at guessing because that's the right answer. But I still posit that it's actually quite hard to know looking at both. There's maybe a slight signal, but could you for certain have told me which one is which? The green lines indicate the minimum sample size from just a standard calculator. Okay, well, let's try again. Probably don't need to get a poll, but just answer in your own mind which you think is the AA and which you think is the AB. And try to imagine that you're actually looking at these dashboards and you're trying to decide, is there a significant test or not? It's pretty hard. It turns out there's actually the second one, right? Which at the time when I stopped the test looked a lot less significant to me, at least. Let's do a fourth one. Here, this is an example where you might think, oh, the effect was super large, so I can stop early. Well, turned out you can't, and I swapped it. The first one is the A/B test, and you see actually the effect was pretty large, and it was nice. The p-value stayed low the entire time, but the A test kind of looked very similar at the end until it didn't. So you sort of have to wait long enough to get the right decision. And then finally, the last one is even more noisy. So who knows which one is which? And give everyone a couple of seconds to think about the answer. And it's the first one again. So up until about 1,000 samples is really hard to tell. So I hope my point is clear that you can't peak early, that the paths of the p-values don't tell you anything about the test, that you really have to stick to your methodology. And I guess that's the takeaway here. Right. So if you really want to stop early and look at your data multiple times, don't, or use sequential methods, right, which are now, as you've seen, getting a lot of emphasis. And I like to emphasize that these examples aren't that contrived, right? I ran this simulation maybe 20 times and took the most egregious 4. So it's not like I went and searched through 1,000 samples or 1,000 different examples for these particular instances. Also, the code will be on the last slide, so you can go try it yourself. You don't have to believe me. Okay. What about pitfall number 2? This is not correcting for multiplicity. So when you run multiple hypothesis tests, you have to adjust the power or the level of alpha that you use. So if you're doing an ABN test, you probably know that you need to do some sort of Bonferroni correction. But I've seen a lot of people look at subpopulations. So they run a test, they find the test is significant, and they zoom into a subpopulation and declare that, oh, look, I found a significant some statistical significance in the subpopulation as well, using the same data. That's looking at the data multiple times, and that's getting multiple hypotheses. You can't actually say anything about subpopulations in a statistically rigorous way. What you can do, though, is to use that kind of exploratory data analysis to suggest further experiments to try it, where you actually then go and get a fresh batch of data and look at that particular subpopulation, but you can't conclude just overall. There's a couple ways to adjust for multiplicity correction. There's Bonferroni, which I mentioned. There's also a weaker notion like false discovery rate. If you have lots of hypotheses that you might be running in parallel, you can try to get an FDR correction, which doesn't guarantee like a type 1 error bound across everything. It guarantees that of the hypotheses that you declare to be significant, only a certain portion of them are false, and that could allow you to have a bit more power. And I left a link for those interested. Finally, pitfall 3 is kind of using the wrong paradigm. So you've seen, at least in the last talk, what a multi-arm bandit is, right? It's when you have multiple options and you're trying to funnel users into the best option as quickly as possible. And we know that multi-arm bandits, at least the default implementation doesn't come with any sort of type 1 error guarantees, but they tend to be faster. So an example, my favorite example of multi-arm bandit is like, which headline do we show on today's front page? Right? You're trying to find that as quickly as possible because the day is only so long and you only have so many users. So in general, when is hypothesis testing appropriate? So hypothesis testing is slower than multi-arm bandits, and it's really appropriate when you actually want false positive control, when you care about having a type 1 error rate that's as small as you need to. And if you're using the results of the experiment to make long-term decisions, right? If you say, find out, the example I have here is that you do a test, you find out that better descriptions are more impactful than better pictures, you're then going to go and give more budget to your writers and not more budget to your photographers. So this decision you're making has a potentially long-term impact. Or if you're trying to use the results of your experiment to guide where you're going to do experimentation next. It's much more important to get these sort of get these answers correct, and hypothesis test is more appropriate in that scenario. But if you're doing something short-term, like if you're just trying to learn the best option on a web page, and knowing what the best headline on your front pages doesn't really tell you that much about what to do in the future, then a bandit is probably the right terminology, because the information about what's the best arm isn't going to impact you that much, and therefore you don't need to be absolutely certain about it. Okay, so I think a little over time, but that's all I had, and I would love to take some questions.
Yeah. I don't know quite how it works with the questions now. I think you can hear us, Alan?
I can, yes.
It should work fine. Any questions for Alan? Do think carefully. Alexander?
Hi, thanks for the talk. And I've got a question regarding causal discovery. So in this, can you hear me?
Yes.
Yeah, so in this case, you have a causal graph, but what happens if you don't? So how would you deal with this problem, and have you experience with this, and how would you go on about it?
So if you have like what people do in the econometric and social sciences, good question, is they look at this. Actually, can I still share my slides? I'm not sure if you can see this, but they have this ignorability assumption, basically. Hold on. This one right here, where you assume that there's some independence when you condition on your covariates. And the hope is that what you basically need is to be able to calculate your propensity score here, which means that the probability of treatment should be determined by just randomness and also your propensity scores. So you would make U, excuse me, excuse me, you would make U have more and more features until you're like somewhat confident that you're actually able to predict the treatment effect from those covariates. So in this example of smoking causes lung cancer, right? This is a kind of a big example throughout all of causal inference, and it drove a lot of these changes in methodology. But before, there used to be hypothesis that, oh, maybe there's a hidden genotype. That's what U is. It's causing an association between your treatment smoking and your response to lung cancer. And you can't adjust for this hidden genotype. But what you could do is maybe adjust for other features. So you would include in your covariates set like a person's age and socioeconomic status and all the other things you think could be a joint cause of smoking and cancer. And eventually you include more and more covariates. And the more covariates you include and still find that there is a causal link, the more strong your hypothesis is. So without a causal model, you can hope that you at least can learn a propensity model by just including as many covariates as you can, and hopefully that like captures enough of the of these unobserved or of these observed confounders that let you still make pretty valid causal inference. But if you have a more complicated graph on more than just 3 variables, then you can learn a graph through expert input if you're in a particular problem domain like biology or chemistry, or you can do experiments, run experiments to try to orient edges of the causal graph. So from observational data, if you can observe everything, observational data allows you to learn the essential graph, which is basically the adjacencies in this graph and the V structures in this graph. And that's just a result from Bayesian learning. And you can do experiments to orient the edges that you don't know the orientation of to be able to ultimately recover a causal graph. But it's an arduous process.
Thank you. And then in the interest of time, I think we should proceed with the last final little bit of the program. So let's take Alan again.
Thanks, everyone.